Here are our notes for Unit 3.7, Capacitance. This is our last section of Unit 3. Capacitance is the ability of a conductor to store energy in the form of electrically separated charges. Okay, so I'm actually going to move to a simulation to show us what this looks like. So here's a simple capacitor. The capacitor is two plates connected by a battery, and the battery acts like a pump. What the battery is going to do is it's going to transfer charge, and you can see the direction of the arrows there. I'm going to start this over. I'm going to go to 0. Start over. I want you to notice the little arrows that pop up. So if I zoom in here, what we're doing is we are pumping electrons. Maybe I need a darker color. We're pumping electrons off of the positively charged plate and pumping them onto the negatively charged plate. So that battery, again, is serving like a pump, an electron pump. And I also kind of think of it like stretching a rubber band. I'm pulling apart these things that are attracting, right? The positive and negative plates attract. And as we pump more and more charges, there's more and more attraction. And this is a way to store energy. We can store energy by the fact that we've pulled these charges apart. It's kind of like in a rubber band. If I pull on a rubber band and stretch it and hold it there, I have energy stored in the elasticity of the rubber band. So let me go back to my notes here. So I'm going to add something to this. I'm going to put the symbol for a battery. And the battery is a pump that moves charges. Those charges, by the way, are electrons. We remember that positive charges can't move. So the battery is a pump that moves charges from positive to negative. And, and this process stores energy in that charge separation. Okay, so capacitance then is defined as the ratio of the net charge on each plate to the potential difference created by the separated charges. So of course we know we've got an electric field here. And that electric field also creates a potential difference. So perhaps I'm just making up numbers here, but let's say that the negative plate is at 0 volts, and let's say that this plate, actually, here I'll do something, maybe, what if I did this with a 9-volt battery? And then I'd have a difference of 9 volts between the two plates. And the capacitance of this would be equal to the charge on each plate divided by that voltage. So that's one way for us to define capacitance. The unit for capacitance is called a farad, which is equivalent to a coulomb per volt. The farad, by the way, is named for Michael Faraday, who was a very influential scientist at the turn of the last century. Okay, there's another way to define capacitance. And the second way to define capacitance is based on the cross-sectional area of the capacitor and the distance between the plates. So if I just make a sketch of, oh, that didn't work very well. Let me see if I can draw a parallelogram. And I'll copy it. Okay, so there's my capacitor. Each plate has an area, and then we've got a distance between the plates. So we're saying that the capacitance can also be defined by the area over the distance And then we also have this constant called the permittivity of a vacuum. The permittivity is a measure of the electric polarizability of the dielectric. In other words, it's a measure of how hard it is to separate these charges on the plates. Now, in class, I did some demonstrations with a Van de Graaff generator, and if you've ever gotten an electric shock, then you've felt what happens when an electron jumps that gap. Again, this number is a measure of how hard it is for an electron to jump that gap. With capacitors, we don't necessarily just put air between them. Often we use a substance that is a insulator, because if I put an insulator between the plates of the capacitor, then I can store more charge. The substance that I put between, the insulating substance, is called a dielectric. If you think about that word, dielectric, two, electric, so we've got those two charges, and we want to maximize how much charge we can put on those two plates. I'm going to go back to Chrome here. So again, now if I increase the voltage, I'm increasing the amount of charge that is pumped between the plates, and changing the plate separation. Actually, look at this, minimizing the separation increases the amount of charge on each plate. In some cases, though, to make this happen, I would need to add a dielectric, because you can imagine if I put these closer and closer together, the negatives are going to want to jump the gap. The other thing I can change is the plate area. The bigger the plate area, the more charge I can store, and therefore more capacitance. So increasing the plate area increases the capacitance. Decreasing the plate separation increases the capacitance. Okay, so we've looked at the demonstration. What's the difference between the capacitor and a battery? So a capacitor, again, is these two charged plates. And we've looked at the definition of that. And a battery is a chemical, it's a way to store energy in chemical bonds. So a battery usually consists of a metal and acid, and the slow reaction between the metal and the acid creates the flow of electric charge. With a capacitor, we've got these two charged plates. So if I were to try to use a battery to light up a light bulb, let's look and see what would happen. So I'm going to charge up my capacitor, and then I'm going to plug it into this light bulb. And what happens is it makes the light bulb glow for a little while, but eventually all of the charge balance goes back to neutral. Those negatives go back to where they started, and the light bulb stops burning. So if I go back to the battery again, I can charge up the capacitor. Notice when I remove it from the battery, the capacitor stays charged. And now if I attach it to the light bulb glows while charge is flowing, but eventually the charge stops flowing. And it doesn't take very long for the charge to stop flowing. With a battery, the chemical reaction can go on for a very long time. Okay, so we can store electrical potential energy in a capacitor. And the formula that tells us how much energy is stored is electric potential energy. Remember, the electric potential energy can also be written as a U, is 1/2 Q times delta V. We can combine this with the definition of capacitance, which I've rearranged to write Q equals CV, and we can also say that electrical potential energy equals 1/2 CV squared. Again, the way that I got that was I took CV and I plugged it in here and then simplified. So let's look at some practice problems. These are pretty straightforward, but they're just intended to get us used to all of these new terms and variables and units. So a 12-volt battery is connected to a 6 picofarad parallel plate capacitor. What is the charge on each plate? So I've identified the voltage and the capacitance. By the way, pico is times 10 to the negative 12. I want the charge. What is the charge? And I'm going to use this formula Q equals CV and plug it in, and I can solve for the charge of 7.2 times 10 to the negative 11th coulombs. Here's another one. A potential difference of 100 volts exists across the plates of a capacitor when the charge on each plate is 400 microcoulombs. What is the capacitance? So again, we've got the voltage. This time we've got the charge, and I can use the formula to find the capacitance, which is for microfarads. Just a little side note, beware that charge has a symbol of Q and it's measured in coulombs. Capacitance has a symbol C and it's measured in farads. So that can be a little confusing because charge and capacitance both start with C, but the symbol for charge is Q and the unit is C. Okay, let's look at a couple more examples. Parallel plate capacitor has a capacitance of 0.2 millifarads and will be operated at 6,500 volts. Calculate the charge stored. So again, we've got capacitance and voltage, and we're going to solve for charge at 1.3 coulombs. And finally, number 4, what is the electric potential energy stored in the capacitor from question 3? So I'm just going to plug in the values into the equation, and I get 4,225 joules. So again, a capacitor is a way to store energy, a device that stores energy. Okay. Let's try to deepen our understanding of electric fields and capacitors. So I'll provide a blank version of this for you to look at, to think about before you listen to these notes. Here we go. Fill in the following statement. Electrical potential energy is blank for a pair of charges, or for a pair of like charges, and blank for a pair of unlike charges. So electrical potential energy is going to be positive for like charges, because think about what happens. To bring these together, I would have to push them together. I would have to do work on the system. And that work would be stored as positive potential energy. This is the reverse, right? These two objects are going to attract each other. Actually, I drew this the wrong way. Pardon me. These are repelling, right? The electric force is repelling, but the force that I would have to exert to push them together would be inward. Okay, conversely, opposite charges attract each other, but the force that I would have to exert would be a pulling apart. So the work required to bring those charges together is negative. Let's look at question 2. If a point charge is displaced perpendicular to an electric field, what is the change in electric potential energy? The force and the distance are perpendicular, so work is 0. So the force due to the electric field is going to be to the right. So when force and distance are perpendicular, we get no work done. Remember that the definition of work is force times distance times the cosine of the angle between them. And the cosine of 90 is 0. Let's try question 3. If the electric field in some region is 0, must the electric potential in that same region be 0? The answer to this is no. Electric field is a vector, therefore electric fields can cancel out. However, electric potential is not a vector. It can be positive or negative based on the charge. So an example, a counterexample to number 3 is if I draw, oh, my iPad's freaking out. if I have two charged, oh, pardon me for a moment, my iPad's freaking out. All right, let's try this again. If I have two charged objects like this, at the point right between them, the electric field would be 0. So right here, the electric field is 0. However, the voltage there, or the potential, is not 0. The reason the electric field is 0 is because if I put a charge there, the force from each external charge would cancel out. The voltage would be KQ over R, and there would be a voltage from each one of these charges. So the total voltage would be twice KQ over R, where R is this distance. So you can have an electric field of 0 with a potential that is not 0. Let's look at question 4. If a proton is released from rest in a uniform electric field, does the corresponding electric potential at the proton's changing location increase or decrease? What about the electrical potential energy? Okay, so by definition, when we have a capacitor, which is two charged plates separated by a distance, the positive plate is always high potential. That's the definition. And the negative plate is always low potential. A positive charge is going to move to the right. So a positive charge is going to move away from the higher potential toward the lower potential. And like a falling object, its potential energy is going to decrease. Now, what about an electron? An electron is going to be attracted to the positive plates. So an electron is going to kind of fall up in a way. It's going to go toward the higher potential plate because, again, the region of potential is defined by the plates, not by the test charge. So the electron's going to move toward high potential, and its electric potential energy is still going to decrease because it wants to go toward the positive charge. The field is doing work on the electron. Let's look at the second number 5. Now it's number 6. The following diagrams show lines for equipotential for a point charge and a uniform electric field, respectively. Find the potential difference in moving a point charge from point A to point B. Okay, so here's A, here's B. So all I'm doing here is looking at the line that is represented by point A. I can see the voltage. The initial voltage is 8 volts. For B, it's 4 volts. And the change is always the final minus the initial. So 4 minus 8 is a change of negative 4 volts. I can do something similar here from A to B. I did A to C for some reason when I did this earlier. There we go. It would be a change of negative 3. If I go from 9 to 6, that's a change of negative 3 volts. Whew. All right.